Okay, the next speaker is Peter Mörters from the University of Bath. Peter's published widely in probability theory, including a book on Brownian motions, and he's also written a number of papers on various probabilistic aspects of networks and processes on networks, and today he's going to tell us about the contact process on the evolving scale-free networks.
Thank you very much, and thanks for the invitation. So as you've heard in the introduction, it's going to be quite a change of topic, and well, that's maybe a little bit unfortunate after the interesting talk we've just heard. So the research I'm going to report about is joined with Emmanuel Jacob from École Normale in Lyon, and I'm also going to report towards the end on some work in progress, which is joined with Emmanuel and Amitai Linker from the University of Chile. So the setup of the talk, I briefly mentioned what the contact process is, a model for the spread of, say, an infection or disease on a network. I'll say which kind of network model I'm looking at, briefly review what we know about the static case, the static process on the network, and then we're looking at the situation when our network is evolving in time. The main purpose of this research is to see what kind of effects we can get when we have a time evolution on the network on top of the process that's taking place on the network. As I said, at the end I will go to some work in progress on more detailed behavior, and hopefully as we go along I'm going to explain informally why these features that we discover, why they are occurring. Okay, so the contact process, also known as the SIS model, is a well-established model for the spread of an infection on a finite graph. Of course not the only one, but the one we will focus on in this talk. So every vertex in our network can be either infected or healthy, and an infected vertex infects each of its neighbors at a fixed rate, which I call lambda, bigger than lambda. That's a positive number, and all the analysis I'm going to do is essentially for lambda going to 0. An infected vertex recovers with a fixed rate which I've set to 1, and most importantly, once recovered, a vertex is again susceptible to infection by its neighbors. That's the simple dynamics that we have, and of course if you want to an important feature here is the susceptibility of a vertex that has recovered from the disease. So there is no immunization in the model. Okay, so this is the process that we're running on a finite graph, and of course this is a Markov model, and it's actually a very simple one from the point of view of Markov chains. Every two states communicate with each other except for the state that everyone is healthy, which is an absorbing state. When everyone is healthy, the infection has died. So somehow after a random finite time, which I call Tx, which is the extinction time, all vertices will be healthy. We will be driven into this state where the infection has died. Okay, so there are essentially two problems you can study here. One is the probability of an infection breaking out when you start with only a small number, say, of infected vertices. This is the question we're not going to look at in this talk. The question that we're looking at is, when the infection has broken out, how long will it take until everybody has recovered? So for simplicity, we start the process always with all vertices infected, and the key question will be, how large is the extinction time? Okay, so we will do this on a finite graph with a large number, capital N, of vertices, and I will speak of quick extinction when the expected extinction time is at most polynomial in the number n of vertices in the network, and I will speak of slow extinction when with high probability the extinction time, or with probability going to 1, the extinction time is at least exponential in the number n of vertices in the network. And somehow behind this is this schematic physics picture of the energy landscape there. So in the quick extinction time, you start with an unstable state, namely everyone infected, and you will relatively quickly move into the equilibrium state, namely everybody healthy. In the more interesting slow extinction time, so that the energy landscapes look like this. There are states which are called metastable states, where there are relatively high energy barriers that stop you from moving directly into an actually more suitable state. It will take a long time until you arrive in this in the equilibrium, because you spend a lot of time in these states here, because you have to overcome these energy barriers. So that is metastability, an effect that can be studied really well in this kind of system. Okay, so that's quick and slow extinction. So that's sort of expressed asymptotically in the number of vertices, but we always look at finite graphs. Okay, so what kind of graphs are we looking at? So we're interested in scale-free networks. So one feature was, of course, you can model a lot of interesting features of a network, and the feature that we would like to sort of put to the front here is the scale-free nature, by which we mean that for very large n and large k, the proportion of nodes of degree k decays polynomially, like some k to the minus tau. And this parameter tau, this is a positive number, is called the power law exponent, and somehow believed to be the sort of order parameter that determines a lot of features of these networks. Apart from that, what we would like to keep the network model as simple as possible, and here is what we do. So the vertex set, we have n vertices. We enumerate them from 1 to n, and this is sort of a ranking with the small indices indicating powerful vertices with large strength. And then we connect every pair of vertices independently. That is the simple assumption that you can make, and the probability of connecting the ith and jth indexed vertex in the network is given by this Pij, which is 1 over n, the network size, times some kernel kappa applied to I over n, j over n, and because this number could be bigger than 1, I'm just cutting off at 1. So the probability is set to 1 if this gives me a number bigger than 1. And there are two kernels that I'm interested in and that will give me scale-free networks, and one is what I call the factor kernel. So that's kappa xy of y is some unimportant parameter beta times x to the minus gamma times y to the minus gamma. So when you think of your favorite scale-free network model, so maybe the configuration model, or Chung-Lu, or Norris-Raitu, and all these models typically have connection probabilities that are at least asymptotically of this form, and the characteristic feature here is that the kernel is a product of a function of x and a function of y. So for example, in the configuration model, of course, the connection probability between two nodes are the product of a feature of one node, namely its prescribed degree, and the feature of the other node, namely its prescribed degree, and this factor property reflects in this factor kernel. So I'm not saying that all these models are precisely this, because the independence is typically violated, but morally these models are very similar, asymptotically they're similar, and I would expect the things I'm saying here are pretty robust in the sense that this represents really this class. There is one other class that doesn't fit into this scheme, and these are the preferential attachment models. So where you build a network by introducing new vertices and connecting them to existing vertices with a probability proportional to the degree or proportional to the degree plus a constant. And in this case, the kernel that you look at is a constant multiple of the minimum of x and y to the power minus gamma and the maximum of x and y to the power gamma minus 1. So this is not factorizing into a function of x times a function of y, and we will see that this makes a big difference. So this is a different paradigm. This is a different kernel that can occur here. So beta is an unimportant parameter. Gamma, which varies between 0 and 1, is an important parameter of the model, and you can see this rather easily when you calculate the expected degree of the ith index vertex by integrating the pi or summing the pij over the j, and then you get that in both cases this expected degree is a constant multiple of n over I to the gamma, and therefore the power law exponent tau is given in terms of this parameter gamma as tau equals 1 plus 1 over gamma in both for both kernels, so justifying why I've given the same name to this parameter. So just for you to remember, power law exponent is 1 plus 1 over gamma. That's the rule, and as gamma varies between 0 and 1, tau varies, or as gamma varies between 1 and 0, tau varies between 2 and infinity, and typically we don't want to look at taus that are smaller than 2 because you have an infinite expected degree, and the models all get a little bit funny in that case. Yes?
I'm not sure I understand. So you assume that you can number the nodes in some way that your function Pig will depend on I over n. So the nodes are all different in that respect?
Yes.
And you have the whole range between 0 and 1?
Yes. Yes. So for example, when I have a model with like Chung Lu, where I have some kind of fitness associated, or maybe a random fitness associated with the vertex, I rank the vertices according to their strength or fittest first, and then a little. Well, I mean, if you do this randomly, for example, the fitness is IID. A little bit of extreme value statistics shows you that this is about what you get for the ith and jth ranked vertex. In the preferential attachment model, the rank would correspond to the birth time. So I would be the ith born vertex, j the jth born vertex. Okay, but if you don't like it, you can just take it as a model. I mean, it's necessarily inhomogeneous, right? That's you don't get scale free from homogeneous. So somehow the vertices have very different strength. Okay, so that's sort of the simplest thing that I can do by defining the static network. I'm going to make it dynamic in a minute, and actually almost everything I'm going to say to the end will be about the factor kernel. Okay, so so we concentrate on the factor kernel. I've written down the probability of connecting the ith and jth ranked vertex again. And when you now run the contact process in the static case on the scale-free network, there is at the beginning of this century, a mean field prediction by Pashto, Sartoris, and Vespignani said that when tau is less than 3, then one expects that the infection survives for a time which is exponential in the network sites for all infection rates. So you always have slow extinction. But when tau is bigger than 3, if the infection rate is small enough, positive but small enough, the expected extinction time is polynomial in the network size. So there exists a quick extinction regime. So there was a sort of a phase transition in our power law exponent predicted at tau equals 3, and from the way that I present this, you can already guess that this turned out to be wrong. And there are, well, several people discovered this. Chatterjee and Durrett have a paper. There's a paper by Berg et al. A little bit earlier, and they have shown this is not true. You can't. This mean field prediction is not accurate. The contact process has always slow extinction. So no matter how small the infection rate is, you always have the metastability. You always have that the infection survives for an exponential time in the network size. And there are refined results in a very nice recent paper by Mountford, Valessin, and Yao. I will come back to that. Okay, so that's the story so far. Now we come to our what we're interested in. Networks change over time, and what we want to understand is how time variability of the network can influence the spread of the disease. So what we're looking at is a situation where the time scales of the network change and the time scales of the disease spread coincide. I'm going to tell you in a minute what the precise ways how we set this up, but sort of the motivation comes from the fact that because you have this difference between the mean field prediction and the actual behavior of the model, you could think of that on the network with a time-dependent structure, you're actually seeing something that if you see something that's different from the static case, it might be more like the mean field case, because the mean field calculation is based on the fact that whenever you look at a part of the network, you resample it afresh, and you don't keep a memory of the network topology. So somehow we were thinking when we started, maybe we will recover the mean field result in a time-dependent network. Okay, so how does the behavior change when the network is evolving? We now put some stationary dynamics on our network, and this is how we do it. So the network or the graph now depends on some time t, and of course the vertex set doesn't change. So we always still have the vertex set as these ranked vertices numbered from 1 to n. At time 0, we form the network by independently connecting every pair ij with this probability pij. I've forgotten to write the minimum 1. And then what we do is we do vertex updating. So there are two things that come to mind immediately. One is vertex updating, the other one is edge updating. Maybe edge updating would be even more natural, but let's start with what we actually do. So every vertex has a clock, and when the clock strikes at exponential random times with a parameter kappa, and when it strikes, say for vertex I, all edges adjacent to I are removed and replaced by new edges that are formed with the same probabilities as before, pij, independently for every j, like that. And of course, this is a dynamics that is stationary. So at every time t, the law of gt is the same as the law that you started with. Okay, so of course, a natural alternative would be to have clocks at the edges and replace the edge by edge ij, remove it when the clock strikes and replace it with a new edge with probability pij. The reason why I'm speaking about this is because it gives more interesting results. But I think both are justified. For example, if you think of your network as some kind of contact, and the dynamics is that you sort of move around, you move somewhere else, you migrate. This migration would lead to you being a different neighborhood, and therefore all your neighbors, all the people you're in contact with, might change at the same time. Of Of course, you can also think of scenarios where they change individually or mixed scenarios. That would all be justified. But this is what the talk will be about. Okay. Anyone? Any comments? Because now I'm going to show the main result. So this is a result that I achieved with Emmanuel Jacob. So we look at the contact process on the evolving network with the factor kernel. At time 0, we assume every vertex is infected. And there are two possibilities. So if tau is less than 4, or if you look at this formula, this is the same as gamma bigger than a third, then whatever the other parameters of the network, there exists some constant such that uniformly in n, the probability that the infection becomes extinct before the exponential time is exponentially small. In other words, with a very large probability, it's going to be exponentially big. We see we see slow extinction in this sense. So for every, no matter what lambda is, you see slow extinction. And if tau is bigger than 4, we have a critical parameter lambda, such that when lambda is less than this critical value, there exists a constant such that the expected extinction time is polynomial, bounded by a constant multiple of n to the gamma times log n. So two observations, and maybe surprising. One, in the evolving network, a quick extinction regime that was not possible in the static case has become possible. Okay. So somehow, in this point, from this point of view, it's bad for the infection if the network changes. But if tau is, but this happens when tau at tau equals 4, and not at tau equals 3, as you would have guessed from the mean field calculation. So there is another effect of at work, which sort of reflects the fact that in the evolving network, the infection has more access to other vertices, and that is sort of something positive, at least compared to the mean field model, on its survival chances. Okay, so I'm going to give you a very quick heuristics why this is true. So this has something to do. Okay, let's look at the let's look at the scale-free network first. So the typical thing about the scale-free networks is that there are vertices of high degree, and I call them stars. In the static networks, the stars can keep the infection alive for a long time, and that works by the following mechanism. If a star gets infected, it has many neighbors, and it typically infects a proportion of its neighbors. So when this star recovers, it will not be healthy for long because it has a large number of infected neighbors, and it will be relatively quickly reinfected by its infected neighbors, and therefore these stars sort of keep the infection on for a relatively long time, and the metastable states in the picture arise when a proportion of the stars become infected, and it's very difficult for them to get rid of the infection. In the evolving network, there is an additional effect, and this arises. So when you have an infected star, what can happen is that this star updates, so it gets a new set of neighbors, and of course before the old neighbors where a proportion of them were infected, but when it gets a new set of neighbors, then you will see sort of we will see the current typical density of infections, and that might be small. If you then recover before you infect your new neighbors, then this effect is destroyed. So if you make an update and then a recovery before there is an infection, you can get out of this state in a way that was not possible in the static network. Similar thing holds when you have this the other way around, when you first have recovery and then update. So, but for our arguments, this way around is much more important. Okay, and So stars it's therefore more difficult for the stars to hold the infection. It happens for a shorter time because this mechanism might kick in, and if the stars are not sufficiently connected, or equivalently, if tau is big enough, this effect can destroy the metastability, and this will happen, as it turns out, when tau is bigger than 4. So the observation here is that updating helps the infection process to get out of metastable states, and therefore it speeds up the extinction. But there is a second effect that goes in the opposite direction. So, okay, the probability that the star does what I've just described as a new effect, has an update and then a recovery before it infects its neighbors, new neighbors, is of order 1 over the degree, because so when you've updated, then you have of the order of the degree neighbors. They all have clocks that work towards an infection, and there is one clock competing with it for the recovery, and the probability that the recovery clock wins is something like 1 over the number of competing clocks, that's the degree plus 1, so essentially of order 1 over the degree. So that's the probability of having a successful recovery. If we sort of forget all the other recoveries. So, and how many neighbors how many vertices does the star infect before a successful recovery? Well, the probability of a recovery being successful is 1 over order 1 over the degree. So for the first success, on average, you have to wait of the order of the degree. Okay, and therefore, so you have order of the degree updates, and at each update you get of order of the degree new neighbors, and therefore an infected star infects of order of the degree squared vertices before a successful recovery. So in the static case, all recoveries are successful, and of course you infect of the order of the degree neighbors. Here you have of order of the degree squared neighbors that you can infect before a successful recovery, and that's where this change in the location of the phase transition comes from, because now you say, okay, this is about infected vertices, so there is a size bias, and what I want for the possibility of a quick extinction is the finiteness of the third moment of the degree, and that happens when tau is bigger than 4. The tail exponent is bigger than 4. Instead of tau equals 3, where we didn't have this square in the static case. So summarizing, updating helps the infection process to infect more vertices, and therefore also slows down the extinction. So the effect of the time variability is not monotone, sort of slows down and speeds up the infection process. Okay, I now move to, in the last 15 minutes, to work in progress, and this is about understanding the metastable phase a little bit better. So for this we look at metastable density. So the idea behind this is that if you have slow extinction, so if the infection stays alive for a long time, then it does this by having a density of infected vertices which is maintained at a certain level up to this very late survival time, at which time it collapses and relatively quickly goes to 0. But the long time scale in which the infection is kept, it will be kept at a certain constant density, and we call this the metastable density. So formally defined, we look at the expected proportion of infected vertices at time t, and we take a time tn, which is going to infinity slower than exponentially, and that ensures that we always stay before the extinction time, and then the limit of the expected proportion of infected vertices at these times If this exists, this limit is then called the metastable density, and of course it depends on lambda, the infection rate, and it should be positive. So here's our first result. The date is 2017 because it's in progress, so not all details have been written up. But okay, so here. So we look at the contact process of the evolving network, and of course we're in the case of the factor kernel, and we start with everyone infected. So if gamma is less than a third, we know we have quick extinction. If gamma is bigger than a third, a metastable density exists. So this kind of heuristic behavior actually is there. And more interestingly, it also has, we can also write something about the asymptotics of this density as lambda goes to 0. So this rho of lambda behaves like lambda to some power, and you don't have to be particularly interested in the exact value of this, numerical value of this exponent, but the interesting thing is that it changes at the point gamma is equal to 2/3. That, by this formula, translates as tau equals 5/2. So at the power law exponent tau equals 2.5, there is a change, and this is reflected in a change of the survival strategy of the infection. This is similar to the result in the result in the static case in the already mentioned paper by Mountford, Valessin, and Yao. So I'm going to quickly explain what the strategies are that allow the infection to survive in a competitive way. So it's a transition of time scales. So the transition occurs. So okay, let's just look at this. So gamma between 1/3 and 2/3, in which case the mechanism is what we call delayed spreading. So you've already seen that the stars can survive recoveries by immediate reinfections by their neighbors, and this allows them to keep the infection on a time scale, and this time scale is, well, I said in one of the previous slides, it's the degree. Okay, so I should. In fact, it's lambda squared times the degree. I've left out the lambda in the previous when I spoke of the orders. So it takes of the order of the degree recoveries before you have a successful one, and then of course the probability of infecting and getting reinfected gives you a factor lambda square, which wasn't important before but is important now. So this A lambda is the role of A lambda is such that the vertices numbered 1 up to A lambda times n. These are the stars, and A lambda is a parameter that goes to 0 as lambda goes to 0. Okay, so this is the time scale on which the stars can keep the infection, and then they can spread the infection to other stars, retaining a skeleton of infected stars, and the density that we get is then given by all the neighbors of this skeleton of infected stars. So there is an A lambda, which is the proportion of stars that we have, and the neighbors getting the proportion of neighbors is the product. There's a degree. This is A lambda to the minus gamma, and a factor lambda for the proportion of neighbors of the stars that you have. And when you plug this in, you get the density that I described. Where does the A lambda come from? Well, the A lambda comes from the fact that the infection, this mechanism has to sustain the infection on the stars. So what you want is, if you look at the proportion of stars that infect other stars, so you look at the double integral over the part of the interval where we have stars, kappa xy times lambda. This is the probability of infecting, and then of course multiplied with the time scale, which we already identified as lambda squared times a to the minus gamma. This should be of constant order, which means that sort of if you have a proportion of stars infected, they infect a proportion, also positive proportion in the next round. Okay, from this equation, for example, in this case, you get how big you can make the set of stars, so that the infection can survive on the set of stars, and then you get these figures. This strategy is no longer effective when gamma exceeds 2/3, because it's important that the time scale that we have here is of bigger order than 1, and at gamma equals 2/3, the numerator changed signs that it's no longer a good strategy. After when gamma is bigger than 2/3, the mechanism will have to operate at time scale 1, so you don't see this holding of the infection in stars anymore, but you have a lot of stars highly connected in this case, so you can just spread to these many neighbors that you have, and then you get this other density. Okay, so this is the transition that you have, and of course these strategies give you lower bounds, and I won't have time to speak about upper bounds yet. But I would like to give you in the last 5 minutes also something about the preferential attachment kernels. So this changes this kappa that was x to the minus gamma, y to the minus gamma, now to something which is not of product form. And this changes the things radically. You see a completely different picture. So if you have the evolving network and with the preferential kernel, no matter what tau or gamma is, you always have slow extinction. So you don't get a phase of quick extinction at all for the preferential attachment model, or for the preferential attachment kernel here. And if you have slow extinction, you can ask for the metastable densities, rho lambda, and they exist, and you have again a change in behavior in this exponent. Lambda goes to 0 of the metastable densities. These are all different numbers, and the change of behavior occurs when gamma is 3/5, or in terms of tau, when tau is 8/3. So at power law exponent, tau is 8/3. You see this change of exponent, and this is again the change of survival strategy that you have. But most importantly, you do not have a fast extinction phase, which is quite remarkable. So, and also this change of exponent is quite different from before. When gamma is less than 3/5, we have the delayed spreading as before. I call it now delayed direct spreading because this is going to change here. Actually, it's important to notice that when gamma is equal to half, the two kernels are the same. And therefore, for gamma equals half, it's important that in that regime you have the same behavior, which we have. So individual stars can now survive. It's the same strategy as before. Individual stars can survive recovery through immediate reinfection by their neighbors, and you keep the infection on the time scale. Now, of course, the kernel changes, and therefore the value A changes, and now the time scale is 1/lambda. So that's always bigger order than 1, and therefore it's always worth having a delay for this kernel. And at this time scale, the star spreads the infection to other stars, and the same calculation. This is always the same. So this is what the skeleton, the density that the skeleton induces on the ordinary, the skeleton of stars induces on the ordinary vertices, and you get this power. But if gamma is bigger than 3/5, there is a better strategy, and that's delayed indirect spreading. So you still have the delay mechanism, so the stars can keep the infection on a time scale bigger than 1. You can check that this is always negative, this exponent. But now the stars don't infect other stars directly, but they infect a lot of ordinary vertices, which then infect other stars. So you have a two-star, you don't go from star to star. In that mechanism, you go from star to some ordinary vertex and then to the star. So it's a two-step mechanism. And if you study preferential attachment, that's quite typical of preferential attachment for small values of tau, that you sort of use the fact that the old guys know all the young ones, and that gives them access to other old ones. So in that case, this is a strategy that pays off when gamma is bigger than 3/5, and that allows you, and you do this on this time on this time scale here, and you get a density, which is yet another exponent, another power of lambda. So these are the two strategies that dominate in the case of preferential attachment, depending on the gamma. Okay, so you see that quite a lot of things are happening due to the time evolution of the network, and there's a relatively rich picture emerging. I don't have time to give you a hint on how we prove the upper bounds, but just quick, there's an interesting coupling and a martingale argument. Thank you very much for your attention.
Any questions?
So in your time dynamics, you have this vertex updating.
Yes.
Is there some sort of intervention or mechanism that could be interpreted as a vertex updating if you are thinking of a spread of disease? When could this happen?
Yes. So for example, what I think of is migration, right? I mean, you have the flu. You're on the bus. You're together with the people on the bus. You leave the bus. You're together with other people. So all your neighborhood changes at once in this situation.
Very small time scale.
Yes.
So
Yeah. Of course, I mean, I'm not saying this is the only mechanism. I mean, you have choices. I mean, I chose this kind of scaling because that's where you see interesting things happening. If you, for example, have an edge updating, you don't see a difference in to the static case. If you do them on the same time scale. So you would have to speed up the time scale of the updating to get interesting results, but we've not done that yet.
What happens
So
here?
your epidemics is more like a flu epidemics, where everybody basically is getting sick
Yes.
sooner or later, not something serious, kind of.
Okay, flu can be serious, but okay, yeah. Well.
I mean,
yes.
not deadly. Let's put it.
Yes. Okay. So maybe I don't want to encourage you to think of this too much as a modeling talk. I mean, I'm not serious about suggesting this model for an actual disease. What I'm more interested in is what kind of effects can come up from the time variability.
And
So
you
more
could
a toy
update
model.
A fraction of your. I mean, you update all your vertices, all your edges. You could update a fraction of them, and you get the same.
Well, I think it could be an interesting answer. Something that we have looked at is to make the update rates depending on the rank of the vertices. So you could make old vertices update quicker or slower, and you've seen 3 strategies. You will get a 4th strategy coming in and have a very nice phase diagram with different things that win in different cases. Yes, but of course updating a fraction of the edges, also an interesting idea. You can play with these things.
Any more questions? Can we thank Peter again for a very nice talk?
Thank you.